Distinguished Research Professor, and also Barney E. Rushing Jr., Distinguished Faculty Member at Texas Tech University in the Department of Chemistry and Biochemistry, and also the Department of Physics. He received his PhD in theoretical physics from the University of California, Berkeley, followed by a chemistry research associateship at the University of Chicago. He is also the recipient of the DOE Early Career Award and the TTU Tribute to Teachers Award. His research interest lies in understanding and solving the Schrödinger equation of quantum mechanics from both foundational and practical perspectives. In 2009, he developed a new theory of quantum mechanics without wave functions, together with an interpretation that has now come to be known as many interacting worlds. He is also the recent author of a conceptual guide to thermodynamics by Wiley Publishing 2014. So please, and now speaking on the topic of misconceptions about quantum physics, please welcome Professor Bill Poirier. Thank you.
Just give you a moment here to get set up. Okay, very good. I don't think I'll be moving around very much, so this might will suffice, I think. Also, I wasn't able to see the laser pointer at all in the last talk, and I was in the front row, so I think it's probably hopeless for me to try to use the laser pointer for you guys in the back. So I'll just try to sort of point to different areas of the screen. Let me first start out by thanking Farzad for inviting me to this event. Also, let me thank John for an excellent presentation, which in some respects serves as a good introduction for my own talk. It's great for me to be here. Actually, as you heard, I got my PhD here at UC Berkeley, so these are my old stomping grounds. As a matter of fact, I used to come up here to the Lawrence Hall of Science parking lot on my motorcycle back in the day and watch the sunsets come up here, which is highly recommended. But today I'm here for a different reason. I'm here to talk about misconceptions about quantum physics. And this is a quite difficult task, I have to say, for several reasons. In part, this is difficult because misconceptions are in the eye of the beholder, right? Everybody thinks a little differently, and that's especially true at Berkeley. And so what it is that you misperceive or perceive correctly, it really varies with the person. I have to make some assumptions about who you are and what you're coming in with. But of course, the main reason why this is a difficult task is because quantum physics is so strange and unfamiliar to everybody that even the experts have misconceptions about it. And of course, one of the most famous experts is this guy in the lower left corner of the screen, Albert Einstein, who had some pretty profound misconceptions. And I say that because there were big misconceptions, but they also led to important new discoveries about quantum mechanics. So, you know, you got to hand it to Einstein. Even when he got it wrong, he got it right in some deeper sense. You know? So, and in particular, that sense it has to do with something called the EPR experiments, which I'll discuss briefly a little bit. So, of course, scientists themselves haven't helped matters much. Over the years, we have debated the meaning of quantum physics, particularly its interpretation, ad infinitum. Keep in mind that quantum physics has been around for almost 100 years. And in some respects, we're still as much in the dark as we were in the 1920s about it, in some respects. Other things we've actually learned, made significant progress with over the years. But the point is that scientists will still argue about this, and sometimes it boils down to bad communication and their own misconceptions. So, you know, we scientists, we're sometimes confused about things, as we also learned in the last talk. But apparently there's some press here. Don't hold it against us too much, but despite your tendency to call us baffled scientists in many press releases and so forth, the fact of the matter is that that's not news, that's our natural state. In fact, Einstein himself said, if we knew what we were doing, it would not be called research. And there's a lot of truth to that. So let's talk about what it was that Einstein didn't know, and what it was that in fact he got wrong about the quantum theory. So Einstein believed in definite things. He believed that at the very small scale, which is a scale in which quantum effects manifest, that particles, quantum objects, have definite attributes, just like objects do on the macroscopic scale of everyday existence. So again, we heard about baseballs in the last talk. Imagine watching a baseball as it's being thrown. Right? At every point in time during its trajectory, you can see exactly where the baseball is, exactly how fast it's moving, all of the other attributes, its size, shape, color, and so forth. Now suppose you weren't looking at that baseball, somebody had thrown it. Wouldn't change anything, right? It would still have those attributes. And that's a classical or macroscopic view of the world. Now what happens on the quantum scale is you can't look at all of the attributes at the same time. You can't know what they are. We'll talk about that later on. And this is not debatable. This is something that was known for a long time in the early days. But what was debated, and still is debated to some extent, is whether those attributes actually exist or not. Those unobserved, unseen attributes that have come to be known as hidden variables. So Einstein believed that these things really did exist, even though we couldn't see them. And so to prove he was right, he came up with a thought experiment. He was good at these thought experiments, and that's what he did. And he came up with a thought experiment that has come to be called the EPR experiment. EPR stands for the three authors on the title, the three authors who wrote the paper on this, Einstein, Podolsky, and Rosen. And so the argument goes something like this. If one were to do this hypothetical thought experiment for real, one would find results that are totally insane, according to the quantum theory. Therefore, the quantum theory must be wrong, because we're not going to see these kinds of insane results in the laboratory. So that was basically his argument. The problem with this, though, is that he didn't actually do the experiment. Right? And had he done the experiment, he would have seen that these insane results that he found completely inconceivable are, in fact, what's observed in the lab all the time. The first time those experiments were done, by the way, was right here at Berkeley in the 1970s. Although by that point, people were convinced of what they would see. Most people were anyway. But you know, this goes to show you that oh really? Oh, apologies. How's that better? No? Better? Okay. Apologies for that. So what am I thinking about? All right. So Einstein was came up with this thought experiment. He was convinced of what would be seen in the laboratory, and he turned out to be wrong. By the way, he thought that the results were so insane that it came to be known as the EPR paradox. And the thing about paradoxes is, here's this quote from Richard Feynman here. A paradox is only a conflict between reality and your feeling of what reality ought to be. All right, so this was the problem. This is the problem with thought experiments. Sometimes you have to go in the lab and do something and find out what's really going on. And one of the themes of this talk, which I'll get to later, is the difference between weirdness and logical contradiction. It's a very important difference to keep in mind when we're trying to understand quantum mechanics. Anyway, so this was what Einstein, it turns out, got wrong, but he got it right because he did point the way to these experiments and to deeper insight about how quantum physics really works. Now, Richard Feynman also had another quote about quantum mechanics. He said, "I think I can safely say that nobody understands quantum mechanics." Now, in case you don't know who Richard Feynman is and what his quantum credentials are, David Merton has this quote about Richard Feynman. He's probably the most gifted practitioner of quantum mechanics and the first generation of physicists to have grown up with it, which is quite high praise. But for our purposes, the real question is this: what hope is there? Right? Einstein gets it wrong. Feynman says nobody can understand it, and he's the world authority on the subject. And physicists continue to argue about this with no end in sight after nearly 100 years. There aren't really too many scientific topics that sort of have that kind of history behind them. So what can I do in a 45-minute to 60-minute lecture to sort of clarify all of this, to make you experts in quantum physics, and at the same time resolve all of this ambiguity that's been with us for the last 100 years? Well, it's a real challenge. And a few months ago, actually, I had lunch with Brian Green, and some of you probably know he's very well known. He's very good at explaining complicated subjects such as string theory to a general audience in a way that makes it accessible for them. And so I asked him, how he was able to do this, what his trick was. And what he said, and I'm paraphrasing here a little bit, but he basically said, explaining string theory is easy. Everybody at least understands the concept of a string. Quantum physics, on the other hand, is the hardest. So that was what I'm charged with here. So the bottom line is that it's not possible. I'm not going to make you all experts. I'm certainly not going to get rid of all of the mystery of quantum mechanics in today's lecture. That's, I think, an impossible task. So what can I do instead? Well, I want to get across a few distinctions so that when you sort of read articles in the popular press and so forth, you do so with sort of a smarter eye. So the first distinction I want you to understand is the difference between experiments, quantum experiments that are done in the lab, what they actually say, versus the theories we come up with to try to explain those experiments. Those are two very different levels of things, and they should be kept separate. So a related distinction is that which we've more or less established as true about quantum physics over the last 100 years or so, versus that which is speculative, or perhaps even flat out wrong. Right? So this is where the misconceptions and so forth come in. So in short, what I'm going to try to do, and this is all I can really hope to do, is to turn you all into smart quantum consumers. And like it or not, there's a big quantum market out there right now. This is a best-selling book on quantum healing that you can learn all about, the connection between quantum healing and mind-body medicine, written by a very famous author whose name will not be mentioned. You can also procure the services that there are professional quantum healers on the market today. And so you can hire one of those, or if you're more of a do-it-yourself type, you can invest in a quantum wand, harnessing the magic power of zero-point energy to, I don't know, make a better cup of tea or something. I'm not quite sure what it does, but it's only $42. And this I love. If you notice at the bottom there, there's this description of the percentage of buyers who enjoy this product. It's 0% because there was only one order price. This is about as quantum as you can possibly get. So in any event, actually probably the more telling number is this one at the bottom of the screen, 37,518. This is the number of quantum-themed books that come up in an Amazon search. And I can promise you those 37,000 books are not mostly written for the use of physicists. These are for the general public. So there's a tremendous interest in this stuff. There's a huge market in quantum at the moment, and it's important that you be a quantum consumer. And for that, you don't need to be an expert, right? You go out and buy a car. You don't have to be an expert in auto mechanics, but you do know how to ask the right questions, and what's important and what's not. Right? And so I'm going to try to do the same thing with you today. I'm going to try to turn you all into smart quantum consumers, so you know what you need to ask, but you don't have to be an expert in quantum mechanics to sort of tell when you're being sold a bill of goods and so forth. Okay, so what I'm going to do in the rest of the talk is kind of go through a lot of the standard aspects of the quantum landscape, things many of you have probably already heard about. I'm going to assume that you've mostly heard about these things. We're going to go through these starting with this simpler ideas and then building up in complexity and difficulty. And although you've heard of these things before, probably I'm going to sort of point out misconceptions as we go, which is probably a new wrinkle. Now, in the interest of time, there are certain very interesting, cool subjects I'm not going to be able to discuss. One of those is the EPR experiments I mentioned earlier. These are very interesting because they tie in with themes of non-locality and entanglement that are very important in quantum mechanics, and that have now been confirmed in these EPR-type experiments. And as I said, started here in Berkeley in the 70s. But unfortunately, to take you through the argument that's needed to understand that is a little bit more advanced than what I have time for today. But hopefully you'll kind of get the flavor from the rest of the discussion. The other thing I'm going to do is I'm going to mostly focus on the non-controversial stuff, right? The stuff that's well understood, that's close to experiment, and so forth. Now, towards the end of the talk, I'll start to get into interpretations of quantum mechanics. What does the theory really mean, that kind of thing. And also popular depictions of quantum physics. And I'll have a few things to say about that as well. So that part of the talk will be a little bit more speculative. But mostly, again, this is a no-nonsense talk. You're buying a car. You want to get past it. You want to understand what you're really getting into. And by the way, for the same reason, I don't have the time to get into the history so much, nor the philosophy so much of quantum mechanics. Not that those are not interesting subjects, it's just they would take us a little bit far afield for purposes of the talk like this. All right, so let's start with the wave-particle duality. If you know anything at all about quantum physics, you know that on a very small scale, objects somehow have wave-like and particle-like attributes. I'm sure you've heard this before. Now, sometimes that gets stated a little bit too strongly as the following misconception. Tiny objects are both waves and particles at the same time. Well, in a conventional sense, that can't really be true. We think of particles, as we heard in the last talk, as essentially points, objects that occupy no space. So they're localized, as localized as you can be in space. Waves, on the other hand, are by definition continuous and spread out in space across many points. So how can something that's always localized and always spread out, how can that be one and the same thing? Well, it really can't. That's what I would argue that this is a logical contradiction. It's not quantum weirdness. It's just not being careful with what you're trying to state. So the more accurate statement is maybe something like this. Tiny objects sometimes behave like waves, and other times behave like particles. Right? So even that bothers me a little bit, to be honest. I think really and truly we have to give up on these concepts. Waves and particles are cherished notions in physics that have been around for a long, long time. But the fact of the matter is that in quantum mechanics, things don't really behave like either one, truthfully. So we don't have something that's kind of a hybrid. It's something different altogether. It's just, we just have to accept that. Okay, so the lesson then, I would say, and I will try to give you these lessons for how to be a smart quantum consumer. So the first lesson for how to be a smart quantum consumer: accept the weird, but don't accept the logically inconsistent. Right? Sometimes people will present the inconsistent. A logical contradiction is a true impossibility. That can't happen. But any amount of weirdness can in principle be tolerable. Now, sometimes when it comes to the wave-particle duality, people make the opposite mistake. Right? They assume, well, there's really no mystery here whatsoever. What are other people getting all hung up about? So, sadly, one example of this, one classic example, is in Isaac Asimov's book, The New Intelligent Man's Guide to Science. By the way, this is also a lesson. Never put new in the title. This book is older than I am. In any event, in this book, he has this quote here. A man may have many aspects. Basically, he's saying that a man can be both a husband and a businessman, and that means his behavior will be different in different circumstances. There's nothing mysterious about that. With all respect to Uncle Isaac, that's not really a good metaphor for quantum physics. There is something very weird going on in quantum physics, particularly in the wave-particle duality. So the lesson here is accept the weird in quantum physics. Don't accept the notion that the weirdness can be entirely explained away. It cannot be. Now, why am I so convinced of this? Because I'm not talking about theoretical explanations. One of the problems with theory is, you can come up with any crazy explanation you want. It's all a dream, right? Who can refute that? Well, you can't really. But experiment. So weird, theoretical explanation is maybe something that we have to, we can't refute, or we have to, in principle, live with, even for very mundane experimental facts. But the thing about quantum physics is that it's the experimental facts, it's the reality in the laboratory that's very bizarre. Okay? So it's not just the explanations, although people do come up with bizarre explanations, but it's what's seen in the lab that's very bizarre. And that point I can't stress enough. And there's no matter of debate or controversy there. So that's why I think the weirdness will never go away. Okay, so I want to talk a bit about the wave aspect of quantum objects. By the way, this is, myself included, are sometimes loose about terminology. I'm going to use the term particle, we heard that in the last talk as well, to talk about quantum objects, even though they behave both like particles and waves under different circumstances. Okay? So even if it's behaving like a wave, I'm still going to call it a particle. So in theoretical physics, we use something called a wave function to describe the wave-like properties of quantum objects. Okay? A wave function may or may not have physical reality. The truth is we don't know. But what we do know is that it's a very handy theoretical construct that gives us a lot of information about what's happening when particles are not being observed. Okay? So when particles are not being observed, quantum particles, in effect what happens is they consider all possibilities. So for example, if you're interested in a particle's position, think of a particle as something that's localized and has a definite position. When you're not looking at it, it somehow or other explores many positions at the same time. So this is what we call a superposition state. And the wave that we use to describe this is sometimes called a wave of probability, because there's some probability that the particle is in any one of these states. But when the particle is not being measured, you don't actually see its probability, or there's no sense in which that word probability really has meaning. It's only the second bullet here. It's only when you actually stop to look at the particle and see where it is that this probabilistic aspect of the wave function comes into play. So the wave function is very important. It plays a dual role. It tells you how things evolve in time when you're not looking at it. And then when you do suddenly decide to look at an object and see where it is, what it does then is it tells you what the probability is that you're going to find the object in any point space. So when you're not looking at it, the wave moves deterministically. There's no question about what it's going to do. When you measure something, though, there's a randomness that suddenly gets introduced that has to do with where you actually physically detect the particle. And that randomness is associated with the probability, which we get from the wave itself. So the wave function serves two purposes, and these two processes are very, very different. Hopefully that's clear from my description. In the second process, when we make a measurement of the random process, this is called wave function collapse, because the idea is something that was kind of spread out everywhere suddenly becomes local, that suddenly materializes in just one place. So, and it should be clear, as I said, this is a very different process from what happens when you don't measure. Needless to say, the part of these two bullets, it's the second bullet that causes most of the problems with regard to interpretation and so forth. And we'll come back to this repeatedly. Okay, so what's the lesson that we learned from quantum probability waves or wave function? The lesson is that quantum physics is all about exploring all possibilities. When they're not being observed, quantum particles explore all possible states available to them, such as available positions in space. Now, if you just look at that phrase, quantum physics is about exploring all possibilities, you might think that that means anything goes. Any law of physics could happen, anything might be discovered. In the next half second, this auditorium could turn into the sun, or any kind of, the rules are so crazy we can't predict what's going to happen. And I want to be very, very clear that nothing could be further from the truth. Okay? Now there is some wiggle room when it comes to interpretations of quantum mechanics, about what's going on, and that's what people debate about. And there are also other areas of physics that are more speculative than quantum physics, where people have to speculate because they don't know what's going on. There's not enough experimental data yet, right? And there's nothing wrong with that. But I want to be very, very clear. Quantum physics doesn't just mean you can make up anything, okay? In fact, it's exactly the opposite. A more accurate statement would be, quantum physics is the most reliably accurate predictive scientific theory ever devised. The most accurate measurements ever made are quantum measurements. The most experimentally accurate predictions made by theory have come from quantum theory. So the point is, if you want to come up with a crazy interpretation, a crazy theory of quantum mechanics, you better agree with all the experiments that have been accumulated over the last 100 years. And that's not so easy to do. You can't just make it up as you go along, as some people will write on the blogosphere about quantum physicists. That's just not at all the case. So the lesson here, any physical theory must agree with experimental observations, or it has to be discarded. And if there are more experimental observations, that makes it harder and harder to do that. Okay, so another aspect about quantum physics exploring all possibilities, even though we don't necessarily, we mean this in this very limited sense of exploring all positions, for example, if you're a quantum particle, and not in suddenly reality completely changing its form from second to second. That's still crazy enough. I can't stress this enough. Not only conceptually does it give us a headache, because things can happen like you see in the cartoon in the lower left, or from this Yogi Berra quote from the right side of this slide. Not only can those things happen, give us, if you like, conceptual headaches, but from a computational point of view, this makes life also very difficult, right? Because you have to, on a computer, somehow explore all these possibilities if you want to simulate a quantum system, which I happen to do for a living, and I can tell you it's a pain. So when I talk like this, the word quantum generates interest and excitement in the audience, but I can tell you in a non-physics scientific audience, it does the exact opposite. People they don't want to have to think about this kinds of things. All right, Heisenberg uncertainty principle. Probably all of you have heard of this before. This is certainly one of those areas that has one of the largest misconceptions associated with it. So I have a whole slide dedicated just to what the Heisenberg uncertainty principle is not. Okay? So what it is not is the following statement. No measurement can be made of a quantum particle without affecting that particle. Now, that's not that that's a false statement, in fact, that's a true statement, but it's true in all areas of physics. If you have an interaction between two parts of your system, then one of them is going to influence the other. So that's nothing too remarkable or unusual. It is true that the Heisenberg uncertainty principle does imply that there are some odd things going on in quantum measurement that aren't true that don't satisfy our classical intuition about measurement, for example. It is certainly true that the particle can be greatly affected, but it's also true that the measurement device itself is even more greatly affected sometimes. Sometimes people don't realize that. The truth of the matter, though, is that it becomes kind of harder to disentangle those two things in quantum physics than in classical physics. But the main point here is kind of like the giant microscope that we saw in John's talk. It's not just a matter, we can't not see quantum systems because we need a better measuring device, a bigger microscope, something like that. There are fundamental limits. Right? This is a fundamental law of nature, if you like, rather than some statement about the limits of our current technology. So that's one main point to keep in mind about the uncertainty principle. And so what does it actually say? And so I've told you what it is, and what actually is the Heisenberg uncertainty principle. What it is to say that there's a fundamental limit to the precision with which we can know both particles' position and its velocity simultaneously. We can't measure them both at the same time. If we know one better, more accurately, then we have to know the other one less well. So this may not sound so strange, but really this gets to the heart of this idea of hidden variables and so forth that I mentioned earlier. Position and velocity are attributes for a baseball. They're well defined throughout its trajectory. But suppose that we start out throwing a baseball, we know initially what its position is, but we don't know its velocity. Think about what that means in the next instant of time. In the next instant of time, because its direction and speed are completely unknown to us, it could wind up anywhere in space. So if it started out as a particle, it becomes a wave, or it becomes delocalized somehow. So that suggests that the uncertainty principle has something to do with the wave-like aspect of quantum physics, which is absolutely the case. It also tells you what happens if you measure one thing too carefully. Right? In the next instant of time, you lose all the information that you had even about that one thing, the particle's position. And that, unfortunately, or fortunately, depending on your point of view, is the way that the quantum world operates. And it's really, the lesson here is this idea that we can't see things in the quantum world the way we can in the classical world. And that's, I think, one of the things that's the hardest to wrap our intuition around. Again, kind of like the elephant example in the last talk. We can't at once, and so that shapes everything. It shapes what questions we ask, what it is that the questions we're allowed to ask. And this can manifest in some bizarre ways. Right? So one of the most bizarre ways that this manifests is in the double slit experiment, which again we also heard about in John's. Now the double slit experiment is an actual experiment. It's been done in the lab many, many times. It's not just a thought experiment. And the predictions of quantum theory are borne out in every case. So I'm going to take you through this because it kind of brings all these ideas together and that we've been discussing so far. But I'm going to start with a sort of a simplified version for pedagogical purposes. We're going to start with a single slit experiment, and we're going to do things classically. So imagine we have Carly Lloyd set up at one end of the field, kicking soccer balls against the wall that has a vertical slit in it, or a hole. All right? And what we're going to do, this is classical single slit, so we can watch every ball that gets kicked. For each ball that gets kicked, we're going to see what happens to it before kicking the next one. So, some of them are going to, well, she's a better aim than that. But anyway, some of them are going to miss the slot, and some of them are going to go through the slit. Right? And those that do go through are going to land somewhere on another wall that we place further back directly behind the first one. Okay. So what we're going to do is over time, we're going to pay attention to where the balls that make it through the first slit, where they land on the second wall. And of course, most of them are going to land directly behind the slit itself. Right? A few of them are going to land on either side. Every now and then you'll have an outlier that lies further out. Okay? So this is a statistical problem. We're building up statistics by doing the experiment over and over again. And assuming that Carly doesn't get tired in the process of doing this, we will eventually build up this type of shape here, describing the probability of the ball landing in a certain position on the far wall. So this is, the usual bell-shaped curve kind of thing. This is what we get. There's nothing mysterious going on. Now let's do the same thing quantum mechanically. So we're going to take Carly and her soccer balls, and we're going to shrink her down to the nanoscale. All right, so we're small enough so that quantum effects start to manifest. And now she's going to kick that same soccer ball. The soccer ball is now a quantum particle. So the instant she kicks it, we know exactly where it is. There it is on the left side of the screen. But after she's kicked it, it becomes some wave-like thing. We don't quite know what happens to it. It makes its way through the slit, and then it hits the far wall. Now when it hits the far wall, we're going to measure where it hits the wall. So now we're doing a measurement of position again. So now that wave that was formed in the first instant now suddenly collapses. Right? And we can say exactly where it is with what probability it's. How do we know experimentally what the probability is? Well, we have to, like any statistics and probability study, you have to do the experiment many times over and over again. So we do the same thing. Right? We do the experiment many times, and we get exactly the same curve that I showed you before in the classical case. Nothing mysterious going on at all. Okay, it's a little weird that we can't see what the particles are doing, but we can easily believe from this experiment that hidden variables exist. Right? That every one of these quantum soccer balls has attributes just like the classical soccer balls. We just can't see them for whatever reason. All right? Okay, so let's up the ante a little bit and consider now the double slit experiment, again the classical version. So now let's imagine there are two slits instead of one. Half the balls go through one, more or less, half go through the other. And so if you build up the distribution that you get in this experiment, you get something that looks like this. Okay, it's bimodal. All that means is we have two peaks, one behind each slit. Right? It's just basically the combination of adding together the result you get from individual slits. It's very straightforward. And this is what you get in the classical double slit experiment. The problem, as we already got an inkling of in the last talk, is that when you do the quantum version of this experiment, that's what you get. So let's pause and think about what this means. Right? At the beginning and the end of the experiment, we're measuring a particle as a particle. It's in a definite place at a definite time. We don't know what happens in the middle. But what this is basically telling us is there are many, many places along the wall where the ball simply refuses to land. It's as if there's some kind of magnetic field driving it away or something, but that's not what's happening. It's a purely statistical thing. How on earth do you get that kind of behavior from a double slit? So this is really the fundamental quantum mystery. If you assume that the ball really does have local behavior, have this sort of what they call local hidden variables. In other words, it essentially behaves like something possible that we can't see. You can't explain this. Okay. And Richard Feynman also has this quote about the double slit. This has in it the heart of quantum mechanics. In reality, it contains no mystery. I mean, that pretty much sums it up. This is the experimental weirdness I talked about before that simply won't go away no matter what you do. Now, what's kind of odd about this is actually not that the pattern is something we've never seen before, but precisely the opposite. Ironically, it's a pattern we have seen before, but in a different context. We see this pattern in the context of wave interference. When we work with waves and we send waves through double slits, again, as we heard about in the last talk. So what this is, but keep in mind that we're only sending one soccer ball through at a time. So it's not like we have a wave of many soccer balls. We have one ball at a time. Yet somehow or other, in the middle, it's either turning into a literal wave, which could be what's happening, or it's becoming wave-like. But somehow or other, the only way you can get this kind of an interference pattern that we know of is if one and the same soccer ball, every single one of these soccer balls goes through both slits simultaneously. Okay. And when we're not looking at it in some strange way. So this is very bizarre. And if you're a physicist or a lawyer, and by the way, when you're doing quantum physics, you often have to be lawyer-like because the particles are very sneaky and they seem to try to defy you at every turn and parse everything you ask of them. So you have to be very careful when you ask when you formulate your questions in quantum physics. Anyhow, let's imagine redoing this experiment. Oh, sorry, there's a little animation that shows you that something, some question mark, turns into 2 and then forms 1 again with fire. Okay, so now let's redo this experiment and put up a monitor at the first wall so that we can see exactly where the particle goes through. What do you imagine we're going to see? Are we going to see one ball going through one slit? Or are we going to see 2 copies of the same ball, one going through each of the 2 slits? Or are we going to see some kind of weird quantum wave? You don't have to guess the answer. I'll tell you the answer. What you see is one ball going through one slit. That's always the case in quantum mechanics. When you look at something, it always behaves very well. It's only when you don't look at it that it misbehaves. So it's one particle going through one slit. So then you ask, well, if I only have one particle going through one slit after all, how on earth do I get a two-slit wave interference pattern? And the answer to that question is you don't. In this context, where you actually decide to measure a particle as it's moving through the first wall, you no longer get that quantum interference pattern at the far wall. So this, again, is a bizarre mystery. But if you think about it, this is the only outcome that makes logical sense. Right? If I did still see that double slit interference pattern, it might seem less weird, but it actually would be a logical contradiction because we now know that the ball is only going through one slit. So you can't get a two-slit interference pattern. So it has to behave this way in order to be logically consistent, even though it's extremely weird. Again, weirdness we can accept, logical inconsistency we can't. Okay. So that's a double slit experiment. As I said, it's been reproduced in the lab many, many times. Going forward, we're going to up the ante a little bit. And we're going to talk about concepts that are a little bit more advanced, a little bit harder to think about, a little bit more weird, certainly more complicated. So there's an important misconception, and this misconception is very important because it's one that physicists themselves often make. Right? So I think it absolutely needs to be clarified. And this is this idea that the quantum wave function describes individual quantum particles. Okay? Based on everything I've told you up to now in this presentation, that would be the impression you would have. I've only talked about single particle systems. And so that would naturally be what you would think. The reality is, though, this thing we call the quantum wave function, whatever it is, describes not a single particle in general, but many particles. It describes the entire quantum system, whatever that is. Right? Now, we're going to come back to this issue of what we mean exactly by the quantum system later on, but for now, just think of the quantum system as the set of particles that are maybe interacting with each other and behaving quantum mechanically. Okay? That pesky question in the sub-bullet, ignore that for now. We'll come back to that later. So if anyone tells you that they're describing the wave function of a particle, you know there's something wrong with that story. Again, as a smart quantum consumer, you know what to watch out for. Don't buy that. Something's fishy. Don't buy that car. And one of the places where you see this, I'm going to take a little excursion to talk about this because it's very topical. One of the places where you see this is in claims of recent experiments to have measured the wave function itself. So if you read these papers carefully, you generally see that the claims that are made are not quite that sensational, but certainly in the press releases that come out around these things, they can be that sensational and even more so. So this is a misconception anyway. You cannot measure a quantum wave function directly in the laboratory. And there's a number of reasons why that's the case. Some of them are quite technical, but one of them should be very clear from what I just said, which is that the wave function does not describe individual quantum particles. It describes many particles. Okay? And in general, it cannot be reduced. The wave function cannot be reduced to single particle description. That just that doesn't work. All right? Now, so a more accurate description of what's really going on in these experiments is the following. And I know this sounds much less catchy, but bear with me. An effective single particle wave function can be mostly inferred from a large sequence of separate experiments on completely different particles. All right? Now, I don't want to take all the wonder of these experiments away. In fact, they're incredible experiments. They're really, really cool. I'm not going to talk about how they work, but if you're interested in this, Google quantum tomography and weak measurement, and you can learn about how these things work. So they're very, very cool experiments, but they don't directly measure the wave function. And one of the things they most definitely do not do is prove the existence of the wave function. Right? You might think, well, if I'm measuring a wave function, then that means it must exist. If I'm measuring something, it must exist. That's not necessarily the case. You can take those experiments and interpret them in a way that doesn't involve wave functions at all. In fact, there are formulations of quantum theory that don't involve wave functions. The wave function approach is very useful, very convenient, but it's not necessarily necessary. So that's not what these experiments are doing. And the lesson here is the wave function cannot be directly observed, which we've known actually since the earliest days of quantum theory. Max Born taught us that, and the lesson hasn't really changed since then. Okay. So fine. So the wave function describes many particles. What then does quantum mechanics say about individual particles within a quantum system? Right? If they're not described by a wave function, how are they described? And so one of the misconceptions that one sometimes sees around this is the following. And I put a little question mark there because there's a certain sense in which this statement might be interpreted as being true. But let me just read the statement. A quantum system forms an undivided whole whose pieces have no separate existence. So this is the kind of statement, you sometimes hear physicists make this kind of statement. It gets used a lot in sort of new age treatments of quantum physics and so forth. One has to be a little bit careful about what one reads into a statement like that. I think it may be a more accurate way to say it is the context, that is to say the environment of a quantum particle influences its behavior in a way that is totally different from our intuition about the physical world. Okay? So in other words, if you thought quantum mechanics was weird for one particle, quantum mechanics is especially weird, even weirder when you have many particles. When you have many particles, you can have a quantum phenomenon known as nonlocality that emerges, right? or particle entanglement. Again, don't have time to talk about this in the way that I would like to, maybe in the Q&A session. But this is a very bizarre phenomenon that you see when you have quantum mechanics of many particles. In a more general kind of sense, it becomes somewhat difficult to distinguish the observer from the observed. We'll address this in a moment when we talk about Schrodinger's cat. But the main thing is that it's difficult to pin anything down. As I said before, you have to be a real lawyer in terms of how you frame and answer questions. And it's very easy to get confused if you're not careful. So the lesson here is that quantum physics, especially when you have multiple particles, is all about context. Okay, where does it all end? Wave function collapse and Schrodinger's cat. Some of you may have undoubtedly heard of Schrodinger's cat. I'll talk a little bit about this next. So we understand that in this sort of conventional view of quantum physics, the quantum system behaves one way, right? It evolves in this deterministic way according to what the quantum wave function does. But then when you make a measurement of that quantum system, which is something that happens outside the system, then you get very different behavior. You get wave function collapse and this random stochastic kind of process that I mentioned. So that's all fine and good if you know how to distinguish the quantum system from everything else in the world or the universe. The problem is we don't really know how to do that. There's no straightforward way to draw a box and say everything inside the box is quantum, everything outside is macroscopic scale or classic. And so this causes a lot of problems because obviously how you decide to partition things up has a huge effect on what happens. And you can take a very extreme view where you draw your quantum box so large that it includes macroscopic objects. Okay, and this gives rise to the Schrödinger cat dilemma, which I'll talk about next. So Schrödinger came up with this idea because, like Einstein, he thought there was something wrong with the quantum theory, so he came up with a different thought experiment, a rather more sadistic one, that involves, as I said, drawing the quantum box around a subatomic particle and a cat, a large macroscopic object, in this case a cat. And what we're going to do is we're going to contrive things so that the state of that quantum particle, and that quantum particle can be, just to keep things simple, in one of two possible states. And in reality, it's in some kind of superposition of both of those states, because we're not looking at it. So what you do is you contrive things within the box so that the state of the cat, which is either alive or dead, becomes correlated to the state of this particle. Okay? But now, since the particle is in a superposition state, that means the cat, too, must be in a superposition state. So the cat must be, according to quantum theory, the cat must be both alive and dead at the same time in some kind of weird superposition way. And of course, we never observe such a thing. When we look at cats, we don't see them as being alive or dead. They're one or the other. Hopefully, usually they're alive. But in any event, that's the reality that we experience. Therefore, according to Schrödinger, there's something wrong with the quantum theory. Okay? So as you can imagine, this thought experiment led to some debate. There were basically two camps in the early days. And the debate centered on one of the following two possibilities. So one school of thought, which is what they call the Copenhagen school, so these people like Niels Bohr and Werner Heisenberg, believe that wave wave function superposition did not persist up to the macroscopic scale, that there must be something else that prevents that from happening. So long before something gets big enough that you can look at it, its wave function is already collapsed, and it only is in one state or another. Therefore, you only see it in one state or another, and that's how they get around this paradox of drawing the box. In contrast to that, you have the hidden variable people like Schrödinger and people like Einstein, who believe that particles were indefinite in states, that they did have existence, and that by the time this sort of got up to the macroscopic scale, you could definitely see this, in the fact that we only see a live or a dead cat. So therefore, quantum theory must be incomplete because there's no such thing as a superposition state for cats. So this is where the debate was in the early days, and things have actually kind of changed since those days. In a sense, neither camp was completely right. But that's because they didn't know all the facts. There are two things that have come to light since then, which the founding fathers of quantum theory didn't really fully appreciate or didn't incorporate into their arguments. One of these is the theoretical development, the other one's an experimental development. So number one, I'll start with the first one, lower bullet here. Even if an observer were considered to be part of the quantum system, other macroscopic objects would still appear to that observer to be indefinite states. So what does this mean? It means that if you draw the box around everything, that doesn't contradict our everyday macroscopic observed reality, right? Because we would still perceive cats to be either alive or dead, even if we ourselves were a part of the quantum system. Right? So that doesn't prove anything necessarily, that we don't see these superposition states. All right? Now, the other one is more remarkable because it's an experimental fact. And what's happened over the course of the last few decades, especially just the last 30 years, is people have started to do these double slit experiments that I mentioned with larger and larger objects. So in the beginning, they used photons and neutrons and electrons, subatomic things. And then would take an electron and would go through a double slit, somehow turn into two copies of itself, interfere with itself, and give you a pattern, right? And then they started to do atoms. And then they started to do molecules, and they got the same results. And then they started to do bigger molecules, to the point where now they're taking buckyballs, like these huge things, fullerenes, C60 molecules, 60 carbon atoms, a bunch of hundreds of electrons, somehow making copies of this thing, sending it through, interfering with itself, and so forth. Actually, there are experiments even more recently that claim to do even bigger things, but those are slightly controversial, so let's just stop at buckyballs. That's far enough. Okay. So this is, I think, something that would have stunned people in the early days, the founding fathers. I don't think anybody realized that this is what they would have seen in an experiment had they done these experiments. So in light of these new facts, where do things stand today? How are we to make sense of what's really going on behind the scenes in quantum physics? And so this is where we get into the interpretations part of the talk, the more speculative part of the talk. So Danger Will Robinson, we're now entering the realm of metaphysics. Okay, so we're crossing the line, if you like, between science and experiment. Science and philosophy. Now, why are we doing this? It's because most of the interpretations that are still viable, that people still talk about, they're all already consistent with experiment. So that means you can't use experiment to tell you which one's right and which one's wrong. Okay. So the interpretations don't make any experimental predictions. What they do is they give you a different way of thinking about things, okay, about what's really going on behind the scenes. And at this moment, we can't really tell which one is right and which one is wrong. Therefore, trying to distinguish amongst them is a matter of metaphysics, not really a matter of science. And there are some, by the way, who think that we have no business as scientists doing such a thing. As you can see from this rather strident quote from Niels Bohr, what cannot be seen should not be discussed in the story. On the other hand, the line between physics and philosophy really is kind of vague where quantum physics is concerned. I mean, you can't really get around that. So my own view is that you have to kind of step a toe over the line or two to make any sense of it whatsoever. And the other thing too is that this is something that you don't see much in, if you like, the foundations community, but it's important in my community, which is a little more practical. The different ways of looking at quantum mechanics offer you practical tools for solving problems that are different and that have something very concrete and tangible and practical to offer. So that's another reason why having multiple interpretations of quantum mechanics and not debating which one is better or which one is worse, which one is more simple, etc., it is actually a worthwhile thing to do. So I'm going to go over just a few interpretations of quantum physics. I'm not going to spend a lot of time on this. I'm certainly not going to give you a comprehensive list, so if you don't see your favorite interpretation, please don't rail at me after the presentation. I'm going to focus on three. They're not even necessarily my favorite three, but the reason I'm going to give you these three is because they relate to what we've been discussing, which is this issue of where do you draw the line vis-a-vis collapse of the wave function. Okay? So I think that'll be a good way for you to get a handle on the differences between these interpretations. All right, so there are three options here. Number one says that collapse happens at some small threshold scale. So this is kind of the old idea. Basically, it says that the true dynamics includes the Schrodinger equation part, which is deterministic, plus some kind of random or stochastic part that, on the small scale, doesn't necessarily cause wave functions to collapse, but as the scale magnifies, gradually makes collapse more and more of a virtual certainty by the time you get up to cat-sized objects. Okay? So these are called collapse theories, and there are a number of people who are working, trying to come up with actual theories, mathematical models that do this. A very popular one is called the GRW model. Penrose has thought about this a bit. I'm not going to get into the details. But this is very appealing because it's the least strange, right? Because it involves the least conceptual stretch. The problem with the collapse theories is they don't seem to be borne out by experiment. Because I can take a buckyball and I can split it in two. Okay? Maybe next month they'll be doing, proteins. A few years after that they'll be doing amoebas. When do we say, all right, we've reached the cat size, we have to accept the fact that these collapse theories aren't really what's going on? So, on the surface of it, it's the most appealing by far, it's the simplest, but does not seem to be supported by experimental reality. But there's still people working on this, it still could be correct. Okay, now there's another idea, number two here, which is one of the ones that gets a lot of play in the popular press, which is that collapse occurs with the first conscious observer, the first consciousness that observes something causes that reality to happen. You can see why that idea appeals to a lot of people. Actually, it's appealed to a lot of scientists as well. Penrose, again, when he was in a different mood. Also, von Neumann, you wouldn't necessarily suspect, like von Neumann, if you know who John von Neumann is, you wouldn't think of him as one who would support this idea. He felt that the buck stopped at the first human observer. But that's a question, right? That you can immediately see the problem with this approach. How do you define consciousness? And though there are people working on this problem, both scientifically and philosophically, we're far from solving that problem. And so again, is a cat conscious, or do you have to be a human being? Of course, the fate of Schrödinger's cat depends on that very question, and we just don't know the answer. And then there's a third option, which is that collapse never occurs. So this is what happens when you draw the box so big, the quantum box, that it includes everything. Now the advantage of this from the theoretical point of view is you don't have to explain how measurement happens. You don't have to explain where you're drawing the box, because the box is around everything. So from the theoretical point of view, everything fits into place really nicely. On the other hand, you have to take with this theory that everything, and I mean everything, is in a quantum superposition state. Right? So everything means all observers, it means all people, it means you, it means me. So this is what gives rise to the so-called many worlds interpretation, or the parallel universe idea of quantum mechanics. So when you hear also multiverses applied in the quantum context, this is what people are talking about. Now again, I'm not going to weigh in on which one of these is right or wrong, or which one is most elegant. I leave that to others to do. But I do want, my job is to point out misconceptions. So I'm going to point out two very, very serious misconceptions. Again, if you're a smart quantum consumer, you need to pay attention, because these are things, many worlds and consciousness and all this, the things you see discussed in the quantum context all the time. So misconception number one, quantum experiments prove, in quotes, the existence of aspect X from interpretation one. For example, you might see a headline, quantum mechanics proves the existence of parallel worlds, right? Just like the LHC was purported to do. That is not true. It is not true because parallel worlds or many worlds is one possible interpretation. It could be right. It's internally consistent. It agrees with experiment. But that's all we can ask of an interpretation. If you satisfy those two criteria, you're internally consistent, you agree with experiment, more power to you. Speculate as much as you like. But because there are alternate explanations that don't involve many worlds, we haven't proven the existence of many worlds. Okay, so the different interpretations, again, because they make the same experimental predictions for the most part, can't be proven or disproven, at least not now. Misconception 2 is even more serious. And this is the following: the different interpretations of quantum mechanics are all true at the same time. So this is really a problem in popular depictions. You'll see in the same breath somebody talk about the quantum consciousness of human observer choosing the parallel reality. No, those are two completely different interpretations. You can't mix and match elements from both into an internally consistent theory. What happens is you lose consistency again, and you wind up with garbage. You wind up not just with weirdness, but with something that doesn't make sense. So one interpretation at most can be right. They can't all be right at once. They could all be wrong, by the way. There's nothing that says any of them has to be correct. Okay, so more accurate statement, each provides a consistent framework on its own that they cannot be mixed. Okay, which brings me to my final topic. Popular depictions of quantum physics, do they inform or just sensationalize? And what I'm talking about here, I'm not talking about sort of the Brian Greene or Neil deGrasse Tyson type presentations that are done by physicists for a lay audience, or multiversal journeys for that matter. I'm talking more about the sort of connection with spirituality and Eastern mysticism and these kinds of things. I have nothing against religion, East or West, or spirituality. And I also think it's perfectly fine, as I said before, to speculate about quantum physics. But nevertheless, there are some trends that you see in some of these popular depictions that, as a scientist, really do bother me, right? Because I think that they cause some harm, that they're misleading. So, and again, I don't want to. There's so many of these things, 37,000 titles. I can't, condemn them all with one, cover them all with a single blanket, right? But two trends that I think do emerge in the following. First of all, quantum physics should not just be for the physicists who firmly believe that. It's part of, if you like, the public domain of popular culture. That's perfectly fine. On the other hand, the reality is mysterious and wonderful enough on its own without the need for embellishing hype. It's already incredible as it is. Why add something that isn't there? Okay, so that's point number one. Point number two, again, speculation is fine, but be clear about what you're doing. Don't hide behind the mantle of hard scientific fact. Right? And I think people who aren't scientists think that science has all the answers. It should be clear from the first presentation in mind, we don't always have all the answers, but that's not really our goal. But people nevertheless have a need to have science, when this gets to the third bullet here, they have a need for modern science to provide, if you like, meaning in their lives and or to rationalize their worldviews. Again, if you follow the blogosphere on this stuff at all, you know exactly what I'm talking about. You see these kinds of things all over the place. All right, now again, there are 37,000 titles. I'm going to pick on just one of them, not because it's the most egregious offender. Actually, in some respects, I like this film in the lower left corner. Nevertheless, when I watched it, on the advice of many students and the fact that people keep asking me about this film over the years, I was so upset with all of these sort of inaccuracies and misleading statements that I had to refrain from throwing my shoe at the screen on multiple occasions. That said, however, something else emerged from watching this that I didn't expect, which is a positive thing. The movie has a very strong message, which I think is a positive, which is that there's more out there than our mundane existence. And this much we know at least. And we shouldn't forget that, nor should we be sort of forced into conventional thinking, conventional lifestyle. We're bombarded every day with advertising and marketing that tells us how to think and act and so forth. Most scientists, of course, know that life isn't that way. But non-scientists maybe don't get that message enough. And so to the extent that that movie sends out that message, I think that's a very good and wonderful thing. Just don't drag quantum physics into it, please. That's not necessary. So I did something slightly less destructive than smashing my television set with my shoe, which was to put together a top 10 list of cringe-worthy quotes from the movie, which are available on request, but I won't show them to you. Okay, I will end with a Calvin Hobbes cartoon that I think very well summarizes some of the challenges of trying to understand and explain quantum physics. And with that, here endeth the lessons. Thank you very much for your attention. Can you shout? I'm not sure I can get the mic.
Yeah, just wanted to say, ask about the double slit experiment. In all cases, the slits are illuminated by the same source. If you have two separate sources for the two slits, it will not make an interference. It would behave more classically if there were two separate sources as opposed to, and I believe that the interference pattern is a construct, of the, and you mentioned the detector, or the observer, is how the radiation affects it. Because if you take two flashlights and shine them past each other, they don't affect, or two lasers, and cross their beams, they don't affect each other when they come through. It apparently requires the observer to see this sort of thing, like you read about it, that it needs an observer. The observer is what the summing, is the grand summing junction of the two sources.
Well, certainly the act of observation has a fundamental effect on what happens. You're right, if you have two different sources, you will not see the interference pattern. You may see, though, something different from the pattern I showed you, because the particles themselves now interact in a more mundane, classical way.
The single source is a construct, and with a double slit experiment is a construct of the entire system, including the observer of the detector.
And that connects to this idea that the wave function doesn't describe the particle. The wave function describes the whole thing, in some sense. Other questions?
I was just wondering, you made that, you indicated that all the books that are out there, and they all, well, you talked about all the books that are out there, and it captures the public imagination. We all want to know how it affects our lives and stuff. And so the things that bear on it, you mentioned philosophy and science duality, and it strikes me as a kind of a similar duality made particle. So I have two questions really. One of them concerns something I read in Scientific American recently, a blog or something online, that the wave particle duality has been solved. It's just the consequence of the uncertainty consequence. So we can all not worry about it anymore. And the second thing was, and I noticed from your writing, this is in your field and stuff, could you comment on quantum reality as affects biological reality? What gives?
Okay, so let's start with the wave particle duality. When you say it's been solved, the question is, what do you mean by solved? So in a mathematical standpoint, it's completely solved. We know exactly what the limits are and how they behave when we do certain things. So there's no mystery there. But there's maybe a deeper mystery about what's going on physically behind the scenes. Right? Now, in terms of how quantum physics affects biological systems, well, this is the case, actually. For a long time, there was a belief that things that affect small things don't affect large things. In other words, back to the Schrodinger's cat idea, if I have some subatomic particles, it can be in a superposition state, but that has no influence over what happens to a cat. Right? It's not so clear anymore that that's the case. And in fact, there are certain biological processes that have evolved that exploit quantum phenomena. So one of these quantum phenomena is this thing, quantum tunneling, again, we heard about in the last talk, which is this idea that if you put a particle inside a jar, it eventually escapes. Okay? Well, there are certain biological processes, such as photosynthesis, that would not work if it weren't for quantum tunneling. So it does have an effect even on large-scale biological things.
Thank you very much. And we